episode of Deriving Formulas. Today we are not going to derive just one formula, but a whole host of formulas that apply to a completely different algebra. They're called split complex numbers for a reason. Complex numbers as I squared equals -1. Split complex is j squared equals to 1. That's the main big difference. Addition, subtraction, multiplication, and division are not very different from each other. Just you have to keep in this definition and the distributive law. What happens to the exponential? However, you can use its Taylor series. And then we can substitute ix here. And here comes the fun part. Now we're going to split the real and imaginary parts. 1 minus x squared over 2 plus x4 over 24, this begins, plus x minus x cubed over 6 plus x5 to the power x5 420 plus dot 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 dot. And we can see that this is the Taylor series for cos x, and then this is sin x, so I sin x. What happens if we substitute j in here? So let's change this a bit, and then we add hooks on all of the j's. We group the real parts together. This time this is plus, since j squared is 1. This times j again, and then plus. And then we group the real terms, and I don't know what I call this, but imaginary. Let's just call it imaginary, because I hate the imaginary term. And you can see two more Taylor series popping up. Turns out these are the cosine hyperbolic and j sine hyperbolic. Let's write this down. This is usually written as chis x, I like to call it that. And how about ejx equals to cos x plus j sine x equals to, let's call it chish x. Isn't it a fun name? Anyway, let's just take away this term. Let's just put it chish. Isn't it fun? It only works in the split complex number system. This function only works in split complexes. It won't work in the complex number system because it's simple. And what about De Moivre's theorem? De Moivre's theorem says that cos x plus I sine x to the power of n equals to cos nx plus I sine nx. You can try proving this theorem if you want, but this is when I discovered the split complex numbers. I tried finding a De Moivre for hyperbolics. Yes, hyperbolics. I tried it with I, couldn't get the double angle formula for the hyperbolics out. So I tried this new imaginary unit, j squared equals to 1. And then I got this formula. Here comes the fun bit. This is especially useful when I try to find multiple angle formulas. Since the exponentials, hyperbolics have their own exponential definition, they don't need their own multiple angle formulas. But you will see this is very useful when we attempt to do hyperbolic summations. Let's write these formulas down. Actually, it's CIS again and chish again. So this is De Moivre. Usually this is also written as CISNX equals to CISNX. Would you look at that? The n went downstairs. Same with chish. Actually it's CJSH, but I like to call it chish. Because we are not using I here, we are using J. And this is especially useful. And how about this? Let's call our J, actually Z, forget it. Z equals to A plus BJ. Z to the power of -1 equals to, wait for this, we're now going to do a reciprocal of a split complex number. Isn't it fun? actually forget it. Let's not do rectangular form. Let's do cis form. Z equals to chish theta, r chish theta, and then 1 over z equals to r chish negative theta, which, as you might know, is the conjugate, z conjugate. So z plus 1 over z equals to, and here we got our special formula, 2r cos theta. Isn't this brilliant? Well, we can omit the r. So now we have our z formula. Z equals to chish theta. Z equals to chis theta. Or we could call it kiss and chish. I don't know what you want to call it. So we have our new host of formulas. Is that my cat? We have an analogous formula for the sign as well. Sorry, I would like to let my cat in. Seems like my cat wants to know about the algebra and the split complexes too. Anyways, let's just continue on. We have an analogous formula for hyperbolic sine and sine. And of course, we have the analogous formulas for this. As you might have guessed, this is very useful when we want to work out integrations of, say, sine to the power of 25. Wait, why would anybody want to do that anyway? Unless you're some kind of math that wants to integrate sine to the power of 25. Then you can use these powerful split complexes formulas, to find the integral in terms of multiple angles. There you go. Lots and lots of formulas for the split complexes. Let's count how many we have now. 1, 2, 3, 4, 5, 6. 6 formulas for the split complexes. 6 formulas for the complexes. And of course, don't forget the norm. The norm is the square of the modulus. We use norm in higher dimensional algebras and algebras such as this one, where numbers can have negative norms. As you can see here, so norm of z equals to a squared plus b squared. And the norm of z, this one here, equals to a squared minus b squared, equals to the sum times difference. That's why I find the split complex numbers so intriguing. The complex numbers have their own unit circle, but the split complexes have their hyperbola. So there you have it, the mysteries of the split complex numbers review. See you, bye!